It moves outward now, away from the sun's warmth, tracing a hyperbola that will never close. By every model, the interstellar visitor designated 3E Atlas should be cooling, quieting, fading back into the dark from which it came. And yet, its coma remains chemically alive. The jets reorganize. The tail structures shift. Something about this object refuses to behave the way frozen relics from deep space are supposed to behave. NASA's most recent observations describe features that, by rights, shouldn't persist this far past perihelion. Rare sun-facing structures that contradict centuries of cometary mechanics. Emission signatures that evolve in patterns no one predicted. Even the trajectory tells a strange story. Small perturbations consistent with outgassing, yes, but the details of what is outgassing and how it's distributed across the nucleus remain unsettled. The geometry won't hold still. The chemistry keeps surprising, and the questions multiply faster than the data can answer them. This is not the story of a comet breaking the laws of physics. It is the story of a comet that operates within those laws, but at the uncomfortable edge of what we thought possible. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. On July 1st, 2025, the asteroid Terrestrial Impact Blast Alert System Telescope in Chile flagged a faint point of light moving against the fixed stars. At first, it was just another designation, another set of preliminary orbital elements fed into the Minor Planet Center's database. But when the calculations finished, the numbers told a story that happens only once or twice in a human generation. The eccentricity exceeded one. The trajectory was hyperbolic. This was not a returning visitor loosely bound to our sun across deep time. This was something passing through for the first and only time. Pre-discovery images, combed from archival data, pushed the timeline back to June 14, 2025, giving astronomers a longer baseline to refine the orbit. The refinement made the conclusion inescapable. 3 Atlas had entered the inner solar system from interstellar space, traveling at roughly 137,000 miles per hour relative to the sun when first detected, a velocity that spoke of origins measured not in astronomical units, but in light years. The timeline that followed became a roadmap for understanding. On October 30, 2025, the comet reached perihelion, its closest approach to the sun, at a distance of approximately 1.36 astronomical units, 203 million kilometers, just inside the orbital zone occupied by Mars. Pulled by solar gravity, its speed had increased to 153,000 miles per hour, a kinetic fact that gave weight to every subsequent observation. Then came December 19, 2025, Earth distance minimum. At 1.8 astronomical units, roughly 270 million kilometers, the comet made its nearest pass to our planet, a geometry that allowed ground-based and space-based instruments to study it with maximum spatial resolution and signal strength. The term interstellar is not speculative here. It is dynamical fact. A hyperbolic orbit means the comet's velocity at infinity remains positive. It will not return. Gaia-based reconstructions of stellar motions over millions of years allow astronomers to trace plausible encounter histories with nearby stars, but the exact stellar nursery from which 3 Atlas was ejected remains uncertain. The humility is embedded in the timeline itself. We know when it arrived, and we know it will leave, but the deep past, and the mechanism that sent it here, remains a matter of inference, not certainty. The observation campaign that followed was unprecedented in its scope and coordination. NASA's Science Mission Directorate assembled a fleet. The Hubble Space Telescope captured sharp, visible light imagery of the nucleus and inner coma. The James Webb Space Telescope turned its near-infrared spectrograph toward the comet, probing molecular emission features invisible to human eyes. TESS, the Transiting Exoplanet Survey, monitored brightness variations on short timescales. SWIFT's ultraviolet instruments mapped the hydrogen cloud that marks water dissociation. And marks water dissociation. SPHERIX, still commissioning at the time, added spectral mapping across multiple wavelengths. Then came the close-in observers. NASA's Parker Solar Probe, ordinarily focused on the sun's corona, captured 3I Atlas between October 18 and November 5, 2025, with its WHISPER instrument snapping roughly 10 images per day as the comet traversed the nearest sun's inner domain. Europa Clipper, en route to Jupiter, turned its ultraviolet imaging spectrograph toward the comet, revealing chemical composition data in a wavelength range not duplicated by any other platform. The European Space Agency's Trace Gas Orbiter at Mars caught the comet in its field of view, adding another vantage point to the growing dataset. On the ground, the network expanded. Gemini North's GMO's instrument, perched atop Mauna Kea, captured post-perihelion color imagery that revealed a greenish glow characteristic of diatomic carbon emission, a signature of organic chemistry being destroyed by sunlight. The observations, timed to track morphological evolution after the comet's closest solar approach, showed structure and visible color gradients that changed over days. Subaru telescope observations, coordinated to coincide with the December 19 Earth distance minimum, added spatial resolution and multiband photometry that allowed researchers to separate dust scattering from gas emission, a distinction critical to understanding what was driving the comet's activity. Time domain surveys contributed their own layer. Pan-star-style photometric bands tracked magnitude variations, while multi-night observing runs at Falk's telescope and similar facilities documented what did and did not vary on hour-to-day timescales, constraining rotational periods and outburst behavior. And then there was the amateur layer, often underestimated, but scientifically essential. CCD, stacking workflows, FITS format data processing, plate-solving smart telescopes operated by dedicated observers around the globe provided constraints on morphology and brightness trends during windows when professional facilities were oversubscribed or weather-bound. The result was a global, continuous observational fabric, spanning wavelengths from radio to ultraviolet, geometries from Earth to Mars to near-solar space, and timescales from minutes to months. Every observation fed into the same fundamental question: what kind of object is this? And the first challenge was foundational: size. Based on Hubble Space Telescope imagery captured on August 20, 2025, astronomers constrained the nucleus diameter to a range between 440 meters and 5.6 kilometers. That factor of 10 uncertainty is not sloppiness. It is the unavoidable consequence of trying to measure a small dark object wrapped in a luminous cloud of gas and dust. But size matters. Mass scales with the cube of radius, and mass determines how much force a given outgassing rate can exert on the trajectory. If 3I Atlas is on the smaller end of that range, the non-gravitational acceleration, NASA reports, small but measurable, implies surprisingly vigorous outgassing for such a compact body. If it is larger, the same acceleration requires less dramatic activity, but raises questions about internal structure and thermal conductivity. The uncertainty propagates forward into every model. Then came the chemistry. James Webb's NIRSpec instrument identified water-related absorption and emission features, along with carbon dioxide and carbon monoxide, molecules that trace different thermal environments and evolutionary histories. But the surprise was the ratio. 3 Atlas appeared unusually cone-rich, a signature that suggests formation in a colder region of a protoplanetary disk, or prolonged exposure to cosmic ray processing in interstellar space, or both. Carbon dioxide sublimates at temperatures lower than water ice under sunlight, which means a cone-dominated comet can remain active at greater heliocentric distances than a water ice comet. That fact alone begins to explain why 3I Atlas was bright and active earlier in its approach than many solar system comets of comparable size. But it does not explain the persistence of that activity well past perihelion, when solar heating should have declined substantially. The molecular story deepened with ALMA. The Atacama Large Millimeter Submillimeter Array, humanity's most sensitive radio telescope for molecular spectroscopy, mapped methanol and hydrogen cyanide across multiple observation dates: August 28, September 18, September 22, and October 25. Methanol production increased as the comet approached the Sun, a trend consistent with thermal sublimation models. But the spatial distribution was anything but simple. ALMA revealed an hourglass-shaped structure in methanol emission, with scale lengths extending far beyond the nucleus itself. Evidence of a distributed coma source where parent molecules fragment into daughter species over tens of kilometers. Hydrogen cyanide, by contrast, showed a distinct depletion in the sunward hemisphere, implying that HCN production was dominated by night-side or polar active regions that only occasionally face the sun. And then came the ratio. The Q to HCN production rate was remarkably high, several times greater than typical solar system comets. Methanol is a tracer of complex organic chemistry. Its abundance relative to simpler molecules like HCN suggests either an unusual initial composition or processing mechanisms, thermal, radiative, or both, that preferentially preserve or generate methanol over other species. None of this, on its own, breaks cometary physics. Comets are heterogeneous objects. Their surfaces can be mantled with insulating dust, hiding volatile-rich pockets beneath. Their rotation can expose different active regions to sunlight on cycles that span hours or days. But 3E Atlas kept accumulating details that sat uncomfortably at the edge of the expected distribution, and NASA's own assessment, calm and precise, reinforced the paradox. The observed trajectory perturbations are small and consistent with ordinary outgassing-driven forces. The mystery is not whether physics can explain the comet. It is which combination of physics, applied where and when, produces this particular pattern. Then came the geometry. Early imaging showed no prominent tail, a surprise for an object moving at such high speed through the inner solar system, where radiation pressure and solar wind should sculpt dust and plasma into the classic cometary arcs that stretch millions of a classic cometary arc, kilometers downwind from the sun. But as perihelion approached and passed, structure emerged. Multiple jets, visible in Hubble and ground-based imagery, appeared to emanate from discrete active regions on the nucleus, their orientation changing over time in a pattern consistent with rotation. The spin period, derived from light curve analysis, converged on roughly 16.16 hours, a timescale that allowed observers to predict when specific jets would face Earth or the Sun. Yet, the jets themselves behaved strangely. Some pointed sunward, a rare and puzzling configuration known as an anti-tail, caused not by geometric perspective effects, as in some historical comet observations, but by actual forward-directed dust emission. For material to be ejected toward the sun, rather than swept back by radiation pressure, requires either very large, high-inertia grains that resist solar forces, or a jet velocity high enough to overcome that pressure temporarily before gravity, and before gravity, light finally bend the trajectory backward. Either scenario demands more kinetic energy than typical cometary outgassing provides. Photometry added another layer of confusion. Brightness surges and unexpected trends appeared across multiple, independent, observing programs. Some could be attributed to changes in viewing geometry, phase angle effects, scattering asymmetries, contamination from foreground stars or background galaxies in crowded fields. But others persisted across different telescopes, different filters, different processing pipelines, real outbursts, or systematic artifacts. Separating the two required meticulous cross-checks, and even then, ambiguity remained. The comet's light curve did not settle into the smooth, predictable pattern expected from a uniformly outgassing, rotating nucleus. Instead, it showed structure, short-term variability on scales of hours, longer-term trends on scales of days, and occasional discontinuities that suggested discrete events, perhaps the sudden exposure of a fresh volatile-rich patch, or the collapse of a dust mantle, or the abrupt cessation of activity in one region as another turned on. And then came the technosignature search. On December 18, 2025, the day before 3 Atlas made its closest approach to Earth, the Breakthrough Listen program pointed the 100-meter Robert C. Byrd Green Bank Telescope, the largest single-dish radio telescope in the world, toward the comet. The observation campaign scanned frequencies between 1 and 12 gigahertz, searching for narrowband signals that would indicate deliberate transmission rather than natural emission. The results, published within days, were unambiguous. No credible narrowband technosignatures localized to the comet were detected. Earlier observations in July 2025, using the Allen Telescope Array, had reached the same conclusion. The fact that such searches were conducted at all speaks to the cultural and scientific disquiet surrounding 3E Atlas. A disquiet not born of tabloid sensationalism, but of careful observers recognizing that this object sits in an uncomfortable region of parameter space. The technosignature null result is important, not because it rules out exotic hypotheses, it was always a long shot, but because it establishes a baseline. If 3I Atlas is generating radio emission, it is doing so at flux levels below the sensitivity threshold of humanity's best instruments, or in spectral modes indistinguishable from natural processes. So what explains the constellation of anomalies? The ladder of hypotheses begins with the mundane and climbs toward the speculative, each rung requiring stronger assumptions and weaker supporting evidence. At the base, heterogeneous volatile layers plus seasonal illumination. If the nucleus is compositionally patchy, coal-rich in some regions, water-ice-rich in others, mantled with dust in still others, then as it rotates, different active areas turn on and off, producing jets that appear to wobble and reconfigure. Add in the comet's unusual tilt, its orbit is inclined and retrograde relative to the solar system's ecliptic plane, and you get illumination geometries that change in ways not typical for ecliptic comets. This tier requires no new physics, only a recognition that comets are messy, and that our models are often tuned to the handful of well-studied short-period comets that dominate the observational sample. One rung up, fractal dust aggregates, and distributed coma sources. ALMA scale length analysis suggests that some molecules, particularly methanol, are being produced not just at the nucleus surface, but across a diffuse region tens of thousands of kilometers wide. This could happen if parent molecules, released from the nucleus as complex ices or macromolecular grains, slowly fragment under solar ultraviolet radiation as they drift outward, creating daughter species far from their point of origin. Such distributed sources would explain the extended methanol emission and the peculiar spatial offsets between different molecular species. Add in the possibility of fractal dust aggregates, fluffy, low-density grains with high surface area-to-mass ratios, and you can account for unusual scattering properties, extended coma lifetimes, and perhaps even the antitail geometry if those grains are large enough to resist immediate radiation pressure sweeping. Still natural, still within known comet physics, but rare. Higher still, an insulating crust and an unusual formation environment. If 3I Atlas spent billions of years in interstellar space, exposed to cosmic rays and the occasional shockwave from a nearby supernova, its surface chemistry could have been processed in ways not seen in solar system comets, which spent their deep history sheltered in the Kuiper belt or Oort cloud. An insulating mantle, perhaps composed of irradiated organic tars or refractory silicates, could delay the onset of water ice sublimation while allowing more volatile species like con to dominate the early activity. Some researchers have suggested that 3I Atlas could be older than the solar system itself, a relic from an earlier generation of star formation. That hypothesis is speculative, but not absurd. Interstellar comets, by definition, formed around other stars, and those stars could be older, younger, or chemically different from the Sun. If true, the comet's composition and structure would encode information about planetary system formation under conditions we can never study locally, making every measurement, no matter how confusing, a window into a laboratory we cannot visit. At the edge of plausibility, reserved for the most speculative discussions and treated with explicit caution, sits the swarm hypothesis. The idea that 3 Atlas might not be a single solid nucleus, but a gravitationally unbound or loosely bound collection of smaller objects traveling in formation. This idea has been raised in specific research contexts, not as a conclusion, but as a hypothesis of last resort when other models fail to account for the observed behavior. It would explain persistent activity, many small objects outgas independently, anti-tail structures, differential radiation pressure on objects of different sizes and albedos could create forward-directed plumes, and the unusual photometric behavior, flickering caused by occultations and scattering variations as subcomponents move relative to one another. But it immediately collides with observational constraints. Hubble's imagery, resolves a single compact nucleus, not a swarm. The technosignature searches found no localized narrowband signals. And, dynamically, maintaining a coherent swarm over interstellar distances, through encounters with stellar radiation pressure, galactic tides, and the sun's gravity well, would be extraordinarily difficult without some form of active station keeping, a mechanism for which there is zero direct evidence. The hypothesis persists not because it is well supported, but because it is a cultural mirror of our uncertainty. When a natural object behaves in ways we struggle to model cleanly, we briefly entertain the uncomfortable question of whether it might not be entirely natural, and then return to the evidence, which remains firmly on the side of a complex, but natural, comet. The story is not over. NASA notes that 3I Atlas remains observable from Earth into spring 2026, a finite but meaningful window for follow-up. But the next major gravitational milestone arrives on March 16, 2026, when the comet passes Jupiter at a distance of approximately 53.6 million kilometers, 0.358 astronomical units, from the gas giant's center. This is not a close encounter in the sense of dramatic tidal disruption or capture. Jupiter's gravity will perturb the comet's trajectory slightly, changing its outbound velocity and direction in ways that depend sensitively on the exact mass and the exact mass non-gravitational forces acting on the comet during the approach. But the encounter offers something else, a change in viewing geometry. Spacecraft near Jupiter, ESA's JUICE mission, though it won't arrive at the Jovian system until 2031, could, in principle, provide radically different vantage points, triangulating the comet's structure and outgassing distribution in ways impossible from Earth or Mars alone. What should happen in each model is testable. If the jets are driven by discrete active areas locked to the rotating nucleus, then rotational light curve signatures and jet position angles should remain coherent, predictable from the spin period. If distributed coma sources dominate, then molecular scale lengths and radial profiles should change as heliocentric distance increases and sublimation rates decline. If the anti-tail is purely a dust grain size effect, then multi-wavelength imaging can measure the scattering phase function and constrain the aggregate structure of those grains. And if any lingering questions about technosignatures remain, coordinated radio monitoring during the Jupiter pass, when the comet is still within range of sensitive instruments, could provide a final, decisive null result, or the first surprise. Astrometry campaigns, like those organized under the International Asteroid Warning Network's Comet program, will continue to refine the orbit. Fuzzy Comet make position measurements harder than for bare asteroids, but the improvements matter. Every additional data point constrains the non-gravitational acceleration vector, which in turn constrains the outgassing distribution, which in turn informs models of internal structure and composition. Multi-wavelength scheduling, radio, infrared, millimeter, remains the fastest path to separating dust, gas, and plasma contributions, and to measuring temperatures, production rates, and molecular abundances with precision that can distinguish between competing hypotheses. The clock is ticking. As 3I Atlas recedes, it dims. Eventually, even Hubble and Webb will lose track of it against the background, and then it will return to the dark carrying its secrets with it. What we are left with is a truth uncomfortable in its simplicity. 3I Atlas is rare, fast, and fleeting. Even with Hubble, Webb, ALMA, Parker Solar Probe, and a global network of ground-based observers, key parameters, the true nucleus size, the internal structure, the exact volatile architecture, remain partially constrained rather than solved. Interstellar objects turn astronomy into forensics, and forensics is slow. Most mysteries, and not with a dramatic reveal, but with better questions. The data will be analyzed for years. New models will be proposed, tested, discarded, or refined. Future interstellar visitors, whenever they arrive, will be compared against this baseline, and the differences will teach us as much as the similarities. The wonder is not the enemy of rigor. It is what keeps rigor alive, what drives observers to stay up through the night and data analysts to check their calculations one more time, what compels an entire scientific community to coordinate across continents and wavelengths for a chance to glimpse something that has never been here before and will never return. 3. Atlas leaves questions behind. That is not a failure of astronomy. It is an invitation to the next chapter, one we will write as the data arrives and the old interpretations give way to new ones, carried forward by the same restless curiosity that first made us look up and wonder what moves among the stars.